do I project from here? Well,
Okay, while they're getting set up, let me just...
yes.
I was just going to introduce you as the director of the International Center for Relativistic Astrophysics Network.
Yes. And it is indeed a pleasure to be here and to go. I'm tempted to say so many things, and as usual, I look back this time to make sure.
I think
make-
we need the microphone.
Where is it?
Most people have been sitting down to speak,
Ah,
or we can
here.
do it like this as
Okay,
well.
just to make sure that that I don't get distracted, I will I will just focus on a recent result which we have obtained last weekend and submitted to APJ about a GRB, and explain why the theoretical interpretation of the data is essential, not only in the analysis of the data, to perform to meaningful way the analysis of the data, but also to ask the right question of what the data can teach us. I mean, this is the crucial point, and I will just give one example. GRB 170405 is the most recent GRB which has exploded as far as yesterday in the universe. It's a beautiful system, and for us that have been studying GRB in the last 40 years, actually I introduced them in, okay, let's not speak about history, in California long ago, but anyway, this is a signal, very rich, very beautiful, at different wavelengths. And what is usually done in the analysis that you can follow in the presentation of a GRB are this analysis in the energy and which direct their attention to the entire GRB as a single system, integrated in time, and try to understand something from these curves. I think this is absolutely inappropriate and does not lead practically to anything. But let me explain a little bit more. After GRB were discovered, and of course a special after the Vela satellite and the Compton satellite, there was a crucial moment in which ASI played a major role with Beppo-Sachs. And Beppo-Sachs was really the masterpiece which united two communities, the X-ray community and the gamma-ray community, together in a satellite. X-ray had been developed by Riccardo Giacconi in US, NASA, fantastic, and we have heard still the open philosophy which was presented here by Mrs. Allen, beautiful this morning. Riccardo gave a fantastic open access to all the world about the Uru, the Einstein mission and so forth, and establish a standard of open data analysis, triggering the interest of scientists and theorists, me included. I was at Princeton at the time, all over the world. So, fantastic story, which led to the identification of the first black hole and so forth and so on. Beppo-Sachs introduced the joining of the two community and the first observation of X-ray and gamma ray in GRBs. The first model which was presented globally all over was this fireball model, in which you have a single system which emits the gamma ray emission in the beginning, and then by shock formation the afterglow in the X-ray. The system expands at almost the speed of light with a very large gamma factor, and this is the most still today, this jetted emission coming out from a single system, still quoted in the literature very often. But then I will, without losing too much time, go to a new hypothesis. A new hypothesis is not new, because some of the co-founders of this new approach are here with me, and they have been working on this for almost 10 years. Jorge Rueda is one of the main interpreters, and Carlo Bianco and many students have addressed a different approach. An approach that the GRB are not single object, but are binary system. And the reason is that some long GRBs, many long GRBs, have a peculiarity, that they occur at a time in which the GRB is emitted, and simultaneously in the same place in space. If they are close enough, you can see also a supernova. If they are not far, you cannot see that, but it exists, and we have now the clear understanding of this. Therefore, the reason I want to give a talk is about how interesting is to examine an alternative model and find out really how gamma ray burst work. Now, in the beginning, we had a few gamma ray bursts. Then the number of gamma ray bursts increased. Then a tentative was made to analyze all gamma ray bursts together to find a standard model for the gamma ray burst of the confirmation of this jetted emission. Our approach has been totally different. Namely, the gamma ray bursts are binaries, and they are in 7 different classes. And you cannot mix them together. They have different progenitors. And if you mix them together, you lose completely the message. Therefore, we focus on one system, the one that are the most energetic long gamma ray bursts, which originate in a binary system here, which is a supernova core explode with a neutron star companion. And what you see in this system is precisely the process of explosion of this supernova accreting into the neutron star companion, and by neutrino emission have overcritical accretion, and creating by accretion on the neutron star a black hole in real time. This is the model of hypercritical accretion, binary-driven hypernova, which was started long ago by Zeldovich and by myself and Wilson, but has been then fully exploited by Jorge, Izzo, Carlo, and all our many students. Now we are at a moment in which we can probe this model. But we have to be very, very careful about how to probe such system. It is necessary to understand that there has been a basic, the astrophysical community has been very, how you said, sportive. They have analyzed the gamma ray burst in arrival time usually. And the arrival time for a gamma ray burst is clearly meaningless because of the detector. Because at CERN you can do an arrival time, but if you look at the different Z in the universe, you cannot classify a system by arrival time. Therefore, it's not surprising that the large majority of the community, not knowing relativistic time coordination, because you need 4 different time coordination to be done properly, miss the key point that if you take the prompt radiation, namely the first moment of emission of the formation of the black hole, and you measure in the rest frame of the source, the prompt radiation is not longer than 100 seconds. And therefore, what happens to the next? What happens to the flare that Professor Osborne beautifully presented this morning? Well, you have to analyze them within the time coordination in general relativity. And it's fantastic that if you do the right coordination, you find a relation between the occurrence of the spike, the successive part of the afterglow, and the final part of the afterglow. I don't want to be too technical, but this is one of the most, in other words, since there is a new epoch on gamma ray burst. If you do the thing properly within cosmology and general relativity, you can understand not all the GRB, but a class of GRB which has a prompt radiation which is standard. And this prompt radiation is followed by another characteristic feature, which is high precision test, the X-ray flare, which occurs around 100 seconds, and then is at a plateau. And this one is the optical emission of the supernova. I don't have the desire to give you all the details. The paper will be tomorrow or the day after in AstroPH. But the most impressive result is that if you do the thing correctly from the point of view of basic theoretical physics, you can understand how the time of the spike and also the width of the spike and also the temperature of the spike can be subjected to a new type of analysis, not qualitative any longer, but an analysis which is high precision test in relativistic astrophysics. Therefore, the first one is the high precision test of the time T90 of the prompt. The second, the high precision test of the X-ray flares occurrence and width and time decay. The third one is the high precision test of the flare arrival time. Now, what this has to do with astrophysics?
Just a few minutes left.
4 minutes. Therefore, what has to do this with astrophysics? This has to do with how to do analysis correctly. But let's do a moment about astrophysics. Well, these are beautiful pictures which have been simulated at Los Alamos and by our theoretical group in Rome, head by Rueda, and by some fantastically bright student we have now working in Los Alamos. It represents the exploding Laura Becerra, the supernova exploding. The black dot is the neutron star. And then the supernova expands, it accretes onto the neutron star. And there you see the supernova explosion in a binary system accreting on the neutron star. And finally, at this point, you have the implosion of the black hole formation and the emission of the GRB. Well, the beauty of our theoretical treatment is that all these stages can be analytically derived. And the picture which comes out, it looks very complex. But at the end, if you analyze all the quantities, it is relatively simple, simple conceptually, difficult to know how to compute this thing, because this needs general relativity, quantum field theory, vacuum polarization, all this field. And we are concerned, not data analysis. We are concerned because the astronomy today is lacking the knowledge of fundamental science. There are very few people who are able to do this analysis in general relativity, and even fewer in making the vacuum polarization analysis of quantum electrodynamics necessary to explain the pair creation interacting with the remnant of the supernova. Therefore, this is the reason why we welcome this initiative with all the energy profused by Paolo Giommi, and we are at disposal with ICRANET to participate. ICRANET means Pescara. You are all invited to come to Pescara, Rome. La Sapienza means Armenia in Yerevan, means Rio at CBPF, and of course Stanford and and Tucson and the people in Los Alamos. Therefore, it's a fantastic moment. If we are able to convey to the politician and to large science audit the new astrophysics which can be obtained if duly analyzed, this will be the growing point of a new science. I already said this message years ago when, when gamma ray bursts were discovered, when we proposed the identification of Cygnus X1 with a black hole in Princeton. But now I am more convinced than ever that all this is reaching a climax and a generality which is no comparison in other field of science. I mean, the gravitational collapse of this system that is represented here, the richness of transforming in real time. I would like you to understand only this, and then I close, if you don't mind. This system lasts less than 100 seconds. In 100 seconds, you have the explosion of the supernova, the accretion in the neutron star, the formation of a black hole, and the formation of a new neutron star. Everything occurs in these 3 minutes. And this is inconceivable for astronomer, traditional astronomer, that like to look at the same system all the time. Here you have a interaction, very, very fundamental, and which can be decoded only if you have graduate students who have learned general relativity, quantum field theory, and scientists who are able not only to be analyzing the data, but analyzing the data with the due understanding of the theoretical background. Therefore, I urge to keep open this collaboration between fundamental science and astrophysics and data analysis, because it's only through that we can offer to the large society a message who can be appreciated and also financed.
Okay, thank you very much. And on that climax, so there are some questions for the speaker.
Well,
Pepe?
I get your point totally, but I think that
It's there.
okay. Oops, sorry. I definitely appreciate your point, but I think there are 2 ways also to think in astronomy, which are kind of complementary. You know, there is the discovery space. You don't know anything about, like when we discovered X-rays. That was a jump in the, yeah, there could have been X-rays. People said, you know, maybe some from the moon, etc. But then you look and you find something. There was no guarantee. You would say, okay, I can do my calculation. They were there. But So there is the discovery space approach, and then there is the physics-based approach, which is your approach. And I think they're both important, and they're both approaches for which what we're doing in the data domain, it's relevant.
Of course.
And it's relevant because we have the data, we have simulation data, we have model, and all of these plays together. We have data mining, but we have modeling as well. So I guess you have your
Yes, I fully agree that there are two aspects. But again, I have to recall an accident I had in Princeton while I was a young assistant professor. The director of the department complained that I had spent $174 in 1 month to call the university, the science, Harvard, and the group of Riccardo Giacconi. The head of the department said, Remo, never mind, go on, call. But these calls were essential, because then to understand that a neutron star could have a period characteristic and a slowing down or a spinning up, depending, shorting. This came in the discussion with Gursky and Riccardo. And the short variability of Cygnus X1 came that way. This has been the great science which has been obtaining the Nobel Prize for Riccardo and the author. We can repeat this, but we have to be ready to be prepared conceptually. The fact that we see in 3 minutes a supernova, a neutron star, creating a black hole in real time, and we see the jet coming out in JEV, this is fantastic. But we need people, and this is my concern, that many of the astronomers today have no the preparation of knowing basic science. They are more qualitative data analysis. And this is the reason we are making an effort with our colleague in South America, in Rio, the Arab PhD in Armenia, to qualify students who can know fundamental general relativity field theory to be able to guide this process. Because there is no way that you can see the effect to understand that you form a black hole or characteristic if you don't have the understanding of the time coordination, for example. And the time coordination has been, you can take all the literature of GRBs, and 90% have missed the time synchronization.
Well,
I mean, it's incredible.
In terms of time, we're running out.